Consider an example. Now in this example, for the given source program, we are expected to show the contents of symbol table, literal table and pool table. Further, we are also required to show the intermediate code generated of variant 1 for this given source program. Now let us jump to the solution. Now in the solution, while solving this example, we will be referring to the machine opcode table, and correspondingly we will try to write it in some intermediate format, that is intermediate code. Now let us consider uh, the first instruction, that is start. But before that, we do need to remember that the initial point lc variable is set to 0. Okay, just a minute, I will just remove all these. Okay, and we will write lc as 0 in the beginning, and now we will start parsing the code. So the first instruction is start. So the referring to the table, we will get to know start is of type assembler directive. So for assembler directives, we need not to perform lc processing, but what assembler does is assembler directive does is it asks the assembler to start generating target code from the given address. As nothing is given in the operand field, so by default it will start generating target code from location 0 only. Now in the intermediate form, I should write start as ad comma its mnemonic info, which is 01. Okay, so ad comma 01 will identify it's a start instruction. Referring to the second line, which is move r. Now move r, if you refer to the table, you will get to know it is having the class imperative statement and mnemonic info is 04. So we do need to perform lc processing. Current lc is 0 and the length of the instruction we are considering is 1. So increment 1 into the lc, 0 plus 1, 1. Next lc is going to be 1. Move r, we will write it in intermediate form as is comma 04. And what about the operands? So the first operand is D register. So we know that we have only 4 registers: A register, B register, C register and D register. Uniquely we identify it by 1, B register by 2, C register by 3, D register by 4. So the D register, we will replace it as 4 comma equal to 9. This is a literal. So what we should do is we should make entry of this in literal table. So I will make entry of 9 in literal table, leaving its address blank right now. Now in the intermediate form, what I should do is I should write it as L, referring to the literal, as it is a literal from the literal table, and followed by its ordinal position in the literal table, which is 0 1. Okay, so L comma 1 will uniquely identify we are referring to the literal 9. Next instruction is move m. Again, if you refer to the table, you will get to know move m is of type imperative statement and its mnemonic info is 05. So we need to perform lc processing as it is an imperative statement, hence current lc is 1. So this is going to be my lc and the length is 1, so add 1 to it and next lc is going to be 2. Now in intermediate form, it is is comma 05. D register, I will write 4 comma, this is m, as it is my second operand, which is a symbol. So I should check symbol table whether I find the entry of this particular symbol m. As it is not there, I will make entry of m, leaving its address blank. And in the intermediate form, I will write it's a symbol from the symbol table followed by its ordinal position 0 1. Next instruction, we are having something against a label field. Always remember, whatever we get against a label field is always going to be a symbol. So loop is a symbol, so we should check symbol table whether we find entry of loop. If not, make fresh entry of loop, leaving its address blank right now. But as this label is this symbol is encountered against a label field, we should update its address straight away, because whenever the symbol get symbol gets in the label field, it is its definition. Okay, so this is the definition, but depending on the type of statement we will have to decide what its address is going to be. So referring to the instruction, it is move r, which is imperative statement, so we do perform LC processing. So my current LC is 2, so the address for loop is going to be 2 only. Okay, in intermediate form, move r, I will be writing it as is comma its mnemonic info, that is 04, b register as 2, then equal to 9, which is again a literal. Now if you see, already we have literal 9 in this literal table, and this is again 9. Okay, now considering the particular sequence of these literals, so all these literals which are being used between start and first occurrence of LTRG, all of these literals, they fall under pool 1 of literals. Okay, so in the same pool, if we get the same literal multiple times, we make only one entry of those literals in the literal table. So for the second occurrence of 9, we need not to make separate entry in the literal table, rather we will be considering it as the same entry. So in the intermediate form, what I should do is I should write L stating its literal from the literal table, and its ordinal position is 0, 1. Now again, the length of this move r, that is imperative statement, is 1, so I should increment LC by 1, so 2 plus 1, 3. Next instruction is origin, which is again an assembler directive. For assembler directive, we need not to perform LC processing. You can refer to the table and try to locate origin. You will find its class as assembler directive. Now what origin does is, this assembler directive, it directs the assembler to update the LC as result of this expression. So what is the result of this expression? It's loop plus 1. So loop is a symbol. We are going to get loop in the symbol table. We need to fetch its address, which is 2 plus 1 equal to 3. So LC is required to be updated to 3, which is already 3, so we need not to do anything. Rather we will be writing this statement in some intermediate form. So origin has mnemonic info 03 and its class is AD. So this will help us to write it in intermediate form. So it is AD comma 03, and loop is a symbol from symbol table. So what I should do is I should write s comma 02, that is second symbol from symbol table, and plus 1 as it is. Now remember, this is assembler directive, so we need not to perform LC processing. At the same time, we need not to do anything else in the LC, because if the result of this expression could have been anything rather than 3, we should have updated the LC. Okay, now moving to the next instruction, which is LTRG. So if you refer the table, you will get to know that the type of or the class of this instruction is AD, that is assembler directive. For assembler directives, we need not to perform LC processing, so I will write nothing against the LC processing. Rather, what LTRG does is it instructs the assembler to allocate memories to the literals prior that particular LTRG statement. That is, that particular pool 1, literals need to be allocated memory. Okay, so first of all, LTRG, I will write it in some intermediate form. So it is going to be AD comma 05. And now this literal in this particular pool 1 was 9, so I should allocate memory to this 9, and while allocating memory to this 9, assembler does the similar adjustment as that of a DC statement. So the current LC is 3, so at location 3 it will allocate memory to this 9, and considering it as a DC statement, we will write it in some intermediate form. So for DC, it is going to be DL, that is declaration statement number 01. Its mnemonic info is 1. you can get to know by referring to the table DC having class TL mnemonic info 1, then followed by the constant 9, so it is C comma 9 referring constant 9. Also we have now allocated space to this literal 9 at 3, so I should update address of this literal 9 as address 3. And again length of this literal is 1, we should update LC by incrementing by 1, that is 3 plus 1 4. Next instruction is having something against a label field which is T, which is going to be a symbol. So we should check the symbol table. If we do not find entry, we will make fresh entry, and at the same time we should update its address because it is arrived at the label field, so it is its definition. Now depending on the type of statement, so add is of type imperative statement, we do perform LC processing, current LC is 4, so I will update LC as 4, and at the same time I should update address of T as current LC, which is 4. And add is imperative statement, referring to the table you will get to know its mnemonic info is 1. A register is my first operand, I should replace it by 1 comma equal to 5 is a literal, I should make entry of 5 in the literal table leaving its address blank, and in the intermediate form I should write L comma 02, that is second literal from the literal table. And the length of the add instruction is again 1, so I should update my LC as by incrementing 1, that is now. Okay, now next instruction is sub, which is again an imperative statement, so I should perform LC processing. So at 5, that is my current LC, sub is is comma 02, its mnemonic info is 02, B register I should write as 2, and equal to 7 is again a literal, so I should make fresh entry of this 7 in the literal table and leaving its address blank, and in the intermediate form I should write L comma 03, that is third literal from the literal table. And again length of the sub instruction, that is imperative statement, is 1, I should update LC as 5 plus 1 6. Next instruction is compare, so referring to the table again you will get to know that compare is of type imperative statement and its mnemonic info is 6. So I should perform LC processing and I should write is comma 06, then B register as 2, and M is a symbol, so I should check my symbol table, locate M, I will get to know its ordinal position is 1, so I should write S comma 01, and the length of again this compare instruction is 1, I should update address LC by 6 plus 1 to 7. Next instruction is branch on control. If you refer to the table, opcode table, you will get to know branch on condition is of type imperative statement and its mnemonic info is 7. So we need to perform LC processing, current LC was 7 and it is is comma 07, LT is a condition code which is its first operand. We know that it is a condition code, total we have 6 condition codes, out of which LT is the first one. So referring to that table we will get to know its mnemonic info is 1. Now remember this one doesn't correspond to the register, rather it is a condition code. Why? Because this is instruction branch on control. Okay, so for branch on control the first operand is always going to be a condition code, not the register. So second operand is back, which is a symbol. Referring to the symbol table we will get to know we do not have entry for back, so we should make fresh entry for back leaving its address blank, and I should update in the intermediate form as s comma the ordinal position of back in the symbol table, which is 04, and the length of this branch on condition imperative statement is again 1, so I should update my LC by incrementing by 1, so it is now 8. Next instruction is LTRG, which is an assembler directive, so I need not to perform LC processing, rather in intermediate form I will write it as AD comma its mnemonic info 05, and this LTRG will instruct the assembler to allocate memory to all those literals in the pool 2, that is between two LTRG statements. Whatever literals are being used, we should allocate memory to those literals. Okay, so literal 5 and literal 7, they belong to pool 2 of literals. Okay, now we get to know that in the first pool we had only one literal 9. So if you see over here, this 9 belong to pool 1 of literals. So in the pool tab, what we should do is the first pool is starting from which literal in the literal table. So it is first number ka literal by which the first pool is starting. Now second pool is starting from literal 5, so its ordinal position in the literal table is 2, and this is the starting of pool 2 of literals. So I should update in the pool table that pool 2 is starting from second pool in the second literal in the literal table. Okay, right now we cannot say what is going to be the starting of pool 3, because yet we do not know whether we do have a pool 3 or not, right? So right now we need to allocate memory to the literal 5 and 7 belonging to the pool 2, because we encountered an LTRG statement. So first of all we have literal 5, so literal 5, and then we have literal 7. Okay, so while allocating memories to these literals, assembler does the similar adjustment as that of a DC statement. Okay, so this is going to be DC 5 and DC 7. So DC 5, the memory will be allocated from the current LC, which is 8. So at 8, so I should update address of 5 in the literal table as 8. In the intermediate form for DC, we can write DL comma 0 1 and the operand as 5, which is a constant, so C comma 5. Okay, similarly the length of this literal is 1, so I should increment LC by 1. Now my LC is 9. For 7 I should allocate the space from 9, so 9, and again DC 7 I should write DL comma 0 1 C comma 7. Okay, and I should update address of 7 as 9, and the length of this particular again is 1, so I should increment LC by 1. Now my LC is 10. Moving to the next instruction, we have back in the label field, so I should just look at the symbol table, locate the entry for back. Now this is the definition of back, so what I should do is I am intended to update its address in the symbol table, but depending on the type of instruction, I cannot straight away allocate the current LC as address of back. Let us consider the type of instruction. This instruction is EQU. If you refer to the table, you will get to know that EQU falls under assembler directive class. Okay, now assembler directives, we do not perform LC processing. Okay, but how to allocate address to back? But this EQU statement instructs assembler to equate the right hand side variable or the expression with or the value with the left hand side. So this will be like back, that is left hand side, will be equal to any expression value or symbol in the right hand side, that is loop. Now what is the address of loop? We should refer to the symbol table. We will get to know loop has its address, so we will fetch it, and we should update address of back as 2. So in the symbol table I will update address of back as 2. Okay, and in the intermediate form we should know the mnemonic info of EQU, which is 4. So I should write AD comma 04 against EQU, and loop is my symbol from the symbol table having ordinal position 02. The length of this instruction doesn't matter because this is an assembler directive, and explicitly we are not going to load this instruction in the memory. So the next instruction is origin, which is again an assembler directive, so we need not to perform LC processing. Rather, this origin will instruct assembler to update the next LC as result of this expression. So the expression is t plus 6, t referring to the symbol table, we will get its address 4. We will fetch it 4 plus 6 equal to 10. So the current LC is going to be 10, and which is already 10, so we need not to worry about it. Okay, but in the intermediate form I should write origin in some intermediate form. Referring to the table, I will get to know origin is AD and its mnemonic info is 03. So I should write AD comma 03, and T is my symbol from the symbol table having ordinal position 3 and plus 6 as it is. Next instruction is multiply, which is assembler directive, which is not an assembler directive, rather it is imperative statement, and for that we do perform LC processing. So my LC is going to be 10, and C register multiply having the mnemonic info as 03. So I should write is comma 03, and C register I should write as 3 comma equal to 8 is again a literal. So I should make entry of this literal. Now remember, this literal, this falls under separate pool because second LTRG occurrence and next is straight away end. All these literals between the LTRG, second LTRG and end, they fall under pool 3 of literals. Okay, so we will make entry of this literal in the literal table, leaving its address blank, and in the intermediate form I will write this literal as L comma 04, that is fourth literal from the literal table. The length of this imperative statement is 1, so I should increment LC by 1. Now my current LC is 11. Next instruction is stop, which is imperative statement. Again we need to perform LC processing, and in the intermediate form it is is comma 00. Next again we should increment LC by 1, that is length of the imperative statement stop is 1, hence next LC is going to be 11 plus 1 12. Next instruction is MDS3. Now this M is arriving at the label field, so it is its definition. So the type of instruction is DS, that is declaration statement. So this declaration statement will help assign M some storage declaration. So how much declaration? So that is stated in the operand field. So 3 memory spaces are to be declared for the symbol M starting from current LC. Current LC is 12. Hence 12, 13 and 14. So these 3 memory locations will be assigned for M, and M will be pointing to the very first memory location of it. Okay, so I should update address of this M in the symbol table, that is 12, and in the intermediate form I should write it as DL comma 02, that is my declaration statement DS, and against 3 I should write C comma 3. Okay, now how should I update my LC? So LC is going to be current LC plus whatever value we have in the operand field of DS statement. So 12 plus 3, so next LC is going to be 15. Okay, then next instruction is end, which is an assembler directive. We need not to perform LC processing. If you look at this, you will find end and its mnemonic info as 2. So I should write AD comma 0 2. Okay, now what about the literal 8? We have not yet assigned memory to this literal. So always remember, memory to the literals is assigned either after an LTRG statement or after the end statement. Okay, so over here we have end statement. So we need to allocate memory to the literal of pool 3 after end. Okay, so similar to what we did earlier, for 8 it will consider as a DC statement. So DC 8. Okay, and my current LC is 15 if you see. Okay, so at location 15 I will write DL comma 01 C comma 8. Okay, and DL comma 01 C comma 8 represents the memory allocated to literal 8, so it is allocated at location 15. I should update address of 8 in the literal table as 15. Correspondingly, this 8 belongs to the pool 3 of literals, so I should write pool 3 of literals is starting from fourth literal in the literal table. Okay, now all the tables are prepared, LC processing is also done, and intermediate code is also written of type variant 1. Okay, now we are done with the pass 1 of 2 pass assembler. Further, this output will be given as an input to the pass 2 of a 2 pass assembler, and further it will generate the target code. Thank you.